Hello, welcome to Advanced Composites. Today is the second day of the ongoing week, that is the ninth week of this course. And today we will introduce a new topic, which is the principle of virtual work. We will discuss this principle in context of our attempt to solve different types of problems related to finite plates. Now, earlier we had shown that we can solve some types of finite plate problems when we are able to select functions for u, v and w in such a way that these functions identically and exactly satisfy all the boundary conditions as well as the governing differential equation. But guessing such functions when plates are of a complicated shape or when the lamination sequence is not very simple, in such situations guessing such functions is most of the times not possible, and in some cases it is not necessarily obvious. So, what do we do in such cases? Well, we use this idea of principle of virtual work, and it enables us to solve a much larger category of problems. So, what we will discuss today is we will actually introduce virtual work method. And here we will discuss two methods. So, one is known as general Galerkin method, and the other one is special Galerkin method. So, once again, what is the advantage of this method? It enables us to solve finite plate problems when closed form solutions are not available or non-obvious. Okay. So, we will start with an example. So, this is a plate. Okay. So, this is 0 0. So, this is my x axis, this is the y axis. The plate is a meters long and b meters wide, and let us say the plate is clamped on all the four edges, and we say that this is such a plate that it is especially orthotropic and so if it is especially orthotropic, then what does that mean? That A16 is equal to A26 is equal to D16 is equal to D26 is equal to 0. And we also say that the lamination sequence is symmetric, and because the lamination sequence is symmetric, the B matrix is 0. So, I will make a small correction here. We will say that the plate is 2a long and 2b wide, not a and b. Its dimensions are 2a and 2b. Okay. So, because of these conditions, because of special orthotropy and symmetry. Actually, it's primarily because of symmetry. So, it's not, I'll correct that. So, because of symmetry, out of plane and in plane problem. These are decoupled. So, I do not have to solve the in plane problem and out of plane problem in a combined way because they are disconnected. So, I can solve the third equation, equilibrium equation separately, and its solution does not influence the solution for first two differential equations which tell us the in plane part of the problem. And we also say that this plate is having some normal load, and that is Q. So, the out of plane problems governing differential equation is del 2 mx over del x square plus del 2 my over del y square plus 2 del 2 mx y over del x del y equals minus q xy. Or if I express this mx, my and mxy in terms of w's, we have shown this earlier, this gives us d11 del 4 over del x4 plus 2 d12 plus 2 d66 del 4 over del x del y square. So, yeah, plus d22 del 4 w over del x del y 4 is equal to q xy. So, this is the differential equation we want to solve, and we want to generate an expression for w which is based on this thing. So, here the method of virtual work is, first step we select. So, what is the unknown in this equation? It is w naught. So, if w naught is unknown, we select w naught, which is a function of sub x and y, such that it satisfies all kinematic boundary conditions. So, this is a significant difference. In the earlier approach, when we were solving for finite plate problem, we were selecting w which satisfied all the boundary conditions. Here we are not satisfying all the boundary conditions, but we are satisfying those boundary conditions which are related to kinematics of the problem. So, kinematics, what does it mean? That which are related to displacements and their derivatives. Okay. So, in the clamped condition, what are the boundary conditions? The boundary condition here is w naught is equal to 0 and del w is equal to 0 on this edge, and also on this edge w naught is equal to 0 and del w over del x is equal to 0. Basically, the slope is 0 in x direction and w is 0 in x direction on this edge, and then on the other two edges w naught is equal to d0 and del w over del y equals 0, and on that edge also w naught is equal to del w over del y is equal to 0. Okay. So, these are kinematic boundary conditions. If there were boundary conditions involving m's or n's or mxy, nxy, then those would be non-kinematic boundary conditions. These boundary conditions, because they are directly related to u, v and w, we call them kinematic boundary conditions. So, we have to select a function which satisfies all the kinematic boundary conditions. In earlier method which we had discussed, the function had to satisfy all the boundary conditions, not only kinematic boundary conditions, and also the governing differential equation. Here we are not saying that the formula or the relation for w need not satisfy the governing differential equation. It need not satisfy non-kinematic boundary conditions, it only has to satisfy the kinematic boundary conditions. So, this is the first step. So, let us guess this. So, we will say that w x y is equal to, let us say w11 times 1 minus cosine pi x over a times 1 minus cosine pi y over b. Let us see whether it satisfies the kinematic boundary conditions. At x is equal to 0, the boundary condition that w should be 0 is satisfied, because when I put x is equal to 0, this term becomes 0. So, that is satisfied. And at x is equal to 2a, I once again put x is equal to 2a. So, cosine of 2 pi is again 1. So, this is also, so this is satisfied. Then what about slopes? At x is equal to 0, the slope dw dx should be 0. So, we see that del w over del x is equal to w11 pi over a minus, this becomes plus sine pi x over a times 1 minus cosine pi x over a, pi y over b, excuse me. So, this is the slope in x direction. So, this is equal to 0 at x is equal to 0, and at x is equal to a, x is equal to 2a. Again, when we put x is equal to 2a, sine of 2 pi is 0. So, again this is equal to 0. Okay. So, all the kinematic boundary conditions, these boundary conditions are satisfied. Now, we can, and similarly other BCs for y is equal to 0 and y is equal to 2b, they are also satisfied. Okay. So, first condition is satisfied. So, this is the first step. So, we have chosen a function which satisfies all the kinematic boundary conditions. We do not care whether the function satisfies the governing differential equation or not, and we also do not care that if there were some boundary conditions not related to u, v and w and derivatives of w, that is, if these boundary conditions were involving n's, m's or nxy, mxy, then the relation for w need not satisfy those also. So, all the kinematic boundary conditions are satisfied. So, now we go to the next step. As w xy need not satisfy the partial differential equation. So, if it was satisfying the partial differential equation, the left side and the right side of the equation would be identical, and the difference between left and right side would be 0. right. So, as Wxy need not satisfy the partial differential equation, there will be an error, So, we designate it as E and we put a cross mark on this. So, what is the error? So, this error is a function of xy and that is equal to d11 del 4 okay. So, essentially how do we calculate the error? We calculate the error by plugging in the governing differential equation. This is our governing differential equation. In this governing differential equation, we plug in the assumed relation for W. So, in this governing differential equation, we have plugged in the assumed relation for W, and because the expression for W need not satisfy the partial differential equation, it may lead to an error, and this error we designated as E and then of course crossed across it. So, this is the error, and this, if the expression for W was identically satisfying the differential equation, this error would be 0, but in this case because it need not satisfy, this need not be 0. Okay. So, this is there, and it is a function of x and y because W is a function of x and y. So, this is the second thing. Now, let us look at what does this error mean. This error has a term Q, and Q is the force in the z direction, distributed force in the z direction. Essentially what this tells us is, so what is the dimension of this error? The dimension of the error will be same as the dimension of Q. So, dimension of error will be newtons per meter square. Okay. So, force per unit area is force per unit area. So, if I multiply this force per unit area by a small element of area, then I will get force in the z direction. Because the dimension of E is newtons per meter square, direction of E is in the vertical direction because Q is in vertical direction. So, if I multiply this by small amount of area or some area, the overall the error will represent an error in force in the z direction. Okay. So, error xy times dx dy is force in z direction. Now, what kind of force is this? If the expression for W was just the right one, that it satisfied the differential equation, this error would be 0, but it is in this case not necessarily 0. So, this is a residual force. So, it is a residual force. In z direction, the residual force in z direction. Now, what we say is that if there is this residual force in the z direction, and if I multiply it by some virtual displacement, and I will explain what is a virtual displacement. So, if this is the residual force in z direction, and if there is some virtual displacement in z direction, then what is the product of virtual displacement and this error force? It will be work, right. So, virtual work in this case will be, if I integrate this error times dx dy. So, this is the force in z direction, and I multiply this by a virtual displacement and I call it W1. So, W was the actual displacement, this is W1, and this is also a function of x and y. So, this is virtual work. So, I am integrating it from 0 to 2a and 0 to 2b, and this force, this virtual displacement is extremely small. So, I multiply it by a parameter epsilon. So, this epsilon you can make it as small as possible, 10 to the power of minus 20, 10 to the power of minus 30, it is just a number, okay. It is just a number. So, I multiply it by a parameter which is extremely small, because these virtual displacements, they have to be extremely small, extremely small. So, this is virtual work, okay. Now, so what is virtual work? Virtual work is the product of error force times virtual displacement, and so this is virtual displacement and this is error force, okay. So, this is the product of this thing, okay. Now, we will explain what is virtual displacement. So, what is virtual displacement? Virtual displacement is any disturbance in plates configuration, any disturbance in plates configuration consistent with its kinematic BCs, consistent with its kinematic BCs. So, what does it mean? So, suppose, so this is the plate, it is clamped on all four sides, and suppose the plate is clamped and it is being acted upon virtual load Q, not virtual load, vertical load Q, it is acted upon by this load Q, then what is so when it is, so this is the plate and it is it's experiencing some external load, and as it experiences load it gets deformed into some position, and in this some position if I disturb this plate very slightly, and that slightly is ensured by this parameter epsilon. What kind of disturbance I can disturb? How can I disturb this? I can disturb it in any way. I can disturb it like this, whatever shape, does not matter, any shape, as long as I do not violate the kinematic boundary conditions, okay. So, any function which does not violate the kinematic boundary conditions. So, in this case, what are the kinematic boundary conditions? That W is 0 on all four sides, and also del W del X is 0 on X is equal to 0 and X is equal to A, and del W over del Y is equal to 0 and X is equal to Y is equal to 0 and Y is equal to B. So, any disturbance in the configuration of the plate which does not violate the kinematic boundary conditions is a virtual displacement, and it is a very small displacement which I ensure through epsilon. So, the principle of virtual work says that the body is going to be in equilibrium if this virtual work is going to be equal to 0. This is the principle of virtual work, okay. So, if the body is going to be in equilibrium, then the integral of this virtual work over the domain of the thing has to be 0. So, now very quickly, so we can, so So, we integrate it from 0 to 2a and 0 to 2b, and what do we integrate? Error times virtual displacement. So, what is error? Error was d11 del 4 w naught over del x4 plus 2d12 plus 2d66 del 4 w naught over del x square del y square plus d22 del 4 del y 4 minus q. So, this is the error, and then I multiply it by virtual displacement, which is epsilon, and any function. So, this is the virtual displacement, and I can choose any function as long as it meets the kinematic boundary conditions. I can choose even the same function, a similar function which I chose earlier, which is this thing, does not matter, right. I can choose the same function, or I can choose a different function anyway. So, I have to choose some function w1, and then I integrate it over the domain, and I set this virtual work to be 0. And when I do this, okay, as when I integrate, what will happen? As I integrate over x and y, what will happen? Now, this w, what is this w naught? We had assumed w to be, w was this thing, okay. So, here w11 is unknown. If we know w11, then we will be fine. So, that is what we are trying to find. So, when we do this integral, what will happen? W is a function of w11 times 1 minus cosine and 1 minus cosine y over all that. So, here as I do the integral, x, y, they will go away, because when I integrate x and y. So, the only unknown in this equation will be w11, and the only, so then I can solve for w11 and get the solution, and that will be an approximate solution. So, this is the overall principle of virtual work. What we will do is, we will actually continue this discussion and solve this problem for a couple of examples, so that you become much more clear about this whole thing. And with that, we close our discussion for today, and tomorrow we will continue this discussion on virtual work. Thank you.